Hello, students. Today we are going to start our journey into modern physics. This is a very important part of your syllabus and it helps us understand the world of atoms, electrons, and light. In this session, we will cover the dual nature of light, Planck's quantum theory, the photoelectric effect, the Compton effect, de Broglie's matter waves, Bohr's atomic model, and the basics of spectroscopy including Fraunhofer lines. By the end, you will see how these discoveries shaped the foundation of quantum mechanics. For centuries, scientists argued whether light is a wave or a particle. Evidence for wave nature, interference, diffraction, and polarization. Evidence for particle nature, the photoelectric effect and the Compton effect. So the truth is, light has wave-particle duality. The energy of a photon is given by the equation E equals h multiplied by nu, where h is Planck's constant and nu is the frequency. Its momentum is given by P equals h upon lambda, where lambda is the wavelength.
Sir, may I ask a question?
Yes, please.
How do we decide whether light behaves as a wave or as a particle?
Very good question. It depends on the experiment. If we perform diffraction or interference, wave nature appears. But in phenomena like the photoelectric effect, light behaves like a stream of particles or photons. Now let's talk about Max Planck's hypothesis. Around the year 1900, there was a big problem with explaining blackbody radiation. Classical physics predicted infinite energy at short wavelengths. This was called the ultraviolet catastrophe. Planck gave a revolutionary idea. He said energy is not continuous but comes in small packets called quanta. The formula is E equals n nu, where n is a whole number. This was the beginning of quantum physics. Now comes the photoelectric effect, explained by Albert Einstein. When light of frequency greater than a certain threshold falls on a metal surface, electrons are emitted instantly. The formula is nu equals phi plus 1 by 2 mv square maximum. Here phi is the work function, which is the minimum energy needed to remove an electron. Also, the stopping potential is given by EVS equals h nu minus phi.
Sir, may I ask why the electrons come out instantly without any delay?
That's because the photon gives its entire energy to one electron in a single collision. If the energy is greater than the work function, emission happens instantly. In 1923, Arthur Compton showed that when X-rays hit electrons, the scattered rays had slightly longer wavelengths. The formula is delta lambda equals h upon mec multiplied by 1 minus cosine theta. This proved that photons carry momentum just like particles. Louis de Broglie asked, if light can behave like a particle, then can particles behave like waves? He proposed that moving particles like electrons have a wavelength given by lambda equals h upon mv. This was later confirmed by the Davison-Germer experiment, where electrons showed diffraction patterns just like waves. Now let us look at Bohr's model of the hydrogen atom. He proposed that electrons revolve in quantized orbits and they do not radiate energy in those stable orbits. Angular momentum is quantized, mvr equals nh upon 2 pi. The radius of the nth orbit is Rn equals n square a naught, where a naught is 0.53 angstroms. The energy of the nth orbit is En equals minus 13.6 electron volt upon n square. Bohr's model explained hydrogen's spectral lines successfully. Spectroscopy is the study of interaction between matter and electromagnetic radiation. In 1814, Joseph Fraunhofer discovered dark lines in the solar spectrum. These are called Fraunhofer lines. They occur because cooler gases in the sun's atmosphere absorb certain wavelengths of light. In X-ray diffraction studies, we use Bragg's law n lambda equals to d sine theta. This helps us determine the structure of crystals. So in this part we studied light behaves as both wave and particle. Planck's hypothesis introduced quantization. Einstein's photoelectric equation proved photons exist. Compton effect showed photon momentum. De Broglie proposed matter waves. Bohr explained hydrogen spectrum. Spectroscopy and Fraunhofer lines reveal atomic structure. That is the end of part 1. In the next session we will discuss radioactivity, Schrödinger's equation, relativity, semiconductors, and lasers. Thank you, students. Revise this carefully. See you in part 2. Jai Hind.